Yeah, so we're just starting that series, and it's this is like the initial very important event, and we want to thank Chen Chen and Haizhong Wang for being ready to make that presentation, and we're hoping to have a lot of people sort of wanting to present their research, because the main goal is to have PacTrans that supports so many students and wants to continue supporting students, help them also disseminate their work so that you can actually show as a student that you've made presentation on your research as you go through the research process. So that's one aspect that has, benefits for the individual student, but also we feel that at PacTrans, we feel with all our partner universities, we have a lot to share, and it's kind of a shame for everybody to stay in their little corner and struggle with their research without sharing it with the larger community. And I want to remind everybody that PacTrans has several universities involved, students from not only University of Washington, that's the lead organization in PacTrans, but also Washington State and University of Idaho, University of Alaska Fairbanks, and Oregon State University. So we have all of these students involved, and that should be, this webinar series is going to be a platform where people can share their research. And so we're just starting that, and I'm very happy to coordinate that and help everybody sort of communicate. But in the long run, people should help themselves to that webinar series, advertise their own work, as well as try to communicate it to the larger world. And so Cole and I actually are working to making the platform easy to reach. Today, I noticed that everybody has to register, which might not be the easiest way to participate, but we will be working, rest assured that we will be working to making participation in a seminar or webinar easier in the future. And then also rest assured that you are all involved in it, and I'm happy to coordinate, but we want to highlight the good research that everybody is doing. So this being said, unless Yinhai wants to say a little more, I think Haishang and Chen Chen, Haishang Wang, the primary advisor for Chen Chen, should lead this first webinar, unless you, Yinhai, have something to say or Cole have something to say.
So thanks, Anne. All I want to say is I highly appreciate Professor Mudong's big effort. It's always more challenging to launch things than keep things going. So this is actually a new event for PacTrans. So the reason we want to launch such a PhD webinar event is because we do believe our PhD students are actually the frontier line persons, doing the research. They are actually the true expert on a lot of the new cutting edge technologies, and we need to give them the platform for them to perform. And also we want them to gain experience and accumulate valuable like credits in the academic world. So that will line them up for the future academic jobs or research jobs in the industry. So we actually got several tens of PhD speakers already lined up. I think that's certainly a good starting for this webinar series. The next thing we need to do is try to let more people know we have such a great PhD webinar platform, and we welcome everyone anywhere in the university in the world, if they are conducting PhD research or recently finished their PhD study and they want to make a talk, and this is the platform. So we don't want professors to be talking here. We also want the student to be organizing them this webinar series themselves. I think that's also a very good training that's normally not available for our regular curriculum. Because this is the first webinar, I just wonder if everyone feel comfortable to turn on the camera and then we take a snapshot, and this could be a memorial event for PacTrans.
Absolutely.
Yeah, so certainly I appreciate that. That's going to make the picture look a lot nicer. Yeah, if you could turn on your camera, please do so. Cole, are you ready to take several maybe snapshots?
Yeah, I wondered, Chen Chen, do you mind unsharing your screen for a moment?
Yes.
So we can capture everyone with their cameras on who are
Right,
willing
sorry
to-
about that.
Nope, that's okay. Yeah, so I'm going to take a few screenshots. So just make a nice face and hold it for a minute or two.
Okay, thanks.
There's one. Let me get another one in here. Just got to save this. And I'm going to take one more just for good measure. Everybody smile. Oh. Great, thank you.
Okay, thanks everyone. And I know you are attending this webinar is actually good support to this new student activity. I highly appreciate that. Thank you very much. Now I want to handle the floor to Haizhong and Chen to perform the webinar today.
Well, thank you, Yinhai. And I just want to say very shortly, and I want to applaud what PacTrans and, under leadership of Yinhai, and also Anne and Cole for putting the effort to make this excellent platform available to students. And I think this is a great event, for students to showcase their research and also even, making friends virtually and creating a network. And this is, a tough week because this is the final week for here at OSU and also at UW. So I think the participation may be a little limited because of the final exam. So keep it short. And Chen is a PhD student graduating.
So Haizhong, I wonder if you want to record this because the webinar needs to be published in.
I've been recording the whole way. We're good.
Oh, okay, that's great. Thank you.
Yeah, I saw that's being recorded. I'll just say very shortly that this research has been funded by National Science Foundation with collaboration with Dr. Michael Lindell from who is also online here, who contribute this significantly, and meeting with team meeting biweekly. Though I want to also just mention that for his significant contribution. And Chen, without further ado, maybe you can take over from here to share the research, and then after that we can address any questions that from the group.
Okay. Yeah. Thank you, Haizhong. Thank you, Yinhai Wang and Nicole and everybody who are arranging this opportunity for us. I feel grateful to have this opportunity to present my dissertation research here. So my name is Chen Chen. I'm a PhD candidate in Oregon State University. Cole, can you see my screen right now? I want to make sure that, okay, cool. Yeah, I have been working more than 4 years on this disaster research. During my PhD journey, I got a lot of help from my committee members, Dr. Haizhong Wang, who is my major professor, Dr. Michael Lindell, he's always here, he's also here, he's from University of Washington, and Dr. David Horwitz, Dr. Dan Cox, and Dr. David Lewis. They are from Oregon State University. So the objective of this research is going to create an interdisciplinary agent-based evacuation modeling framework. The unique feature of this framework is integrating social natural engineering system. The purpose of doing that is to improve the life safety, specifically in Cascadia Subduction Zone. So in today's presentation, I'm going to introduce the background of this research and the motivation of why we create this framework. And I'm going to introduce more details of this framework. Then I'm going to talk about how did we implement this framework in communities in Cascadia Subduction Zone. Within this section, I'm going to show you how do we use questionnaire survey and the evacuation drill method to collect the social system, the data to integrate into this, our simulation model along with engineered system and the natural system. At the end, I'm going to introduce some of the potential application of this model and who can benefit from this model. A little bit background of this research. Cascadia Subduction Zone is a convergent plate boundary that stretch about 1,000 kilometers from North California all the way to Vancouver Island, Canada. And this fault has a rupture probability of 7 to 25% in the next 50 years on average, as scientists predicted. And this rupture can potentially cause magnitude 9 earthquake and tsunami with waves of 10 meters that strike the coastal communities within 20 to 40 minutes. So it is very important for us to be better prepared for the next big one. People use 2011 Tokyo earthquake and tsunami in Japan as an analogy to describe the potential impact of the earthquake and tsunami in Cascadia Subduction Zone. So I'm going to show you a video showing what happened in an intersection when the tsunami came in Tokyo. So as you can see that when the car, people see the tsunami come inundated, they turn around and go to opposite, try to evacuate. And you can see that the devastating tsunami swallowed everything and destroyed everything. So as you can see the video that when the tsunami inundated, it involved 3 systems, a natural system, social system, and engineered system. So these 3 systems overlapped each other and interdependent on each other. So it is very difficult for us to only analyze one system without considering the other 2. So in disaster science, we're looking for an interdisciplinary approach that can simultaneously handle the 3 systems together. So that is our motivation to create our framework. So in this framework, we are going to integrate the 3 systems data into our interdisciplinary evacuation model, as shown in the middle. So the 3 systems, one is a natural environment, and another one is built environment, which we normally refers to engineered system, and also people's and households' protective decision actions. And those are the social and human systems. And specifically, this framework detailed how do we use the PADM model as a guideline to integrate the protective decision and action into our model. So PADM, Protective Action Decision Model, is a social psychology model that describes how an individual react, make a decision based on the information of a disaster received, and how do they react to that information. So there are 3 important data aspects to collected informed by PADM model. The first one is environment, social aspect, and behavioral data aspect, and psychological aspect. So after we collect those data, we're going to use those data to quantitatively model 7 critical components of the household protective decision and actions. So those 7 critical decision actions are warning receipt, the mailing process, the evacuation decision, so evacuation mode, what kind of mode they're going to choose to evacuate, the evacuation decision, evacuation destination, the route choice, and also the movement and the speed. So After we integrate those quantitative model to the interdisciplinary interdisciplinary evacuation model, we can use different means to validate and calibrate this model. So one principle take out from this framework is that the output of the PADM model is going to be the input of the evacuation model. So after the model is validated and calibrated, we can use this result from the model to inform different programs in the 4 phases of disaster. That is hazard mitigation, emergency preparedness, emergency response, and disaster recovery. Each program in the 4 phases has its own very practical objectives. So we are going to take those practical objectives, reiterate through the first step of the data collection in order to make our model more beneficial and useful for practitioners. So those are an overview of this framework. So I'm going to show you how do we implement this framework in detail. So we choose Coos Bay in Oregon as our study community. The reason we do that is because Coos Bay is the largest coastal communities in Oregon. And this community is very vulnerable because 25% of the residents live in the inundation area. And many people still living lower income situation. 22% are senior, older than 65, and this community is built on a peninsula area that 3 directions of the peninsula are surrounded by water, and there are several water dams that is also vulnerable and it may be damaged after the earthquake. So at first, I'm going to show you the visualization of our interdisciplinary agent-based evacuation model. So the reason we use agent-based evacuation model, agent-based model is a class of computational model that can simulate the actions of agent and the interactions of agent, and it can also handle different data layers together. So this model has the unique features that is suitable for our purpose. So this is a GUI of our model. On the left side, you can see this is a Coos Bay, and the green dots represent the resident's location. So each resident is an agent, and each agent have their own decision-making process. They can choose the behavior, and they can choose how they evacuate and when they evacuate. And the blue dots represent the evacuation destination, and the black line represent the transportation network. If you can see, barely the yellow area represent the bay water and the potential inundation area. So on the left side will be the ocean. On the right panel, we have different bar to monitor how many people successfully evacuated, how many people get caught by the tsunami. So I'm going to show the video of when the model is running. So when people receive earthquake information warning or environmental cues, they are starting to evacuate. So as you can see that the green dots agent tended to yellow and dark yellow because they start to evacuate. They choose either walk or drive to evacuate. And as you can see that in the monitor, there are more people successfully evacuate, and until 15 minutes, you can see that the water start to inundate from the west side of this peninsula from the Pacific Ocean. And so when we hit to about oops. Sorry, but I have to play it again. So when we hit to about 20 minutes, you will see that the waves start to inundate on the west side of this peninsula, and the wave get into the Bay Area, and all the way it will go into the Bay Area and inundate on the east side of this peninsula. As you can see that majority of this mortality is happening on the west side of the peninsula. It makes logical sense because this side is the waterfront. And so this is a visualization of our agent-based evacuation models. And then I'm going to introduce how do we build this model. So we integrated 3 systems into this model. First one is engineered system. In engineered system, we include crew space, transportation network, and population distribution. Transportation network, we collected this data from OpenStreetMap and Google Map. And population distribution, we collected from the census data. And the next one is natural system. We integrate the tsunami inundation data we get from Dongami, and also the elevation DEM data we get from NOAA. More importantly, we include the social system and the human system data, integrate those information to inform the agent behavior in this model. So I'm going to show you how do we collect the social system data, that is people's protective action decision. So we use 2 methods to collect the protective action and the decision data from multiple communities along the Cascadia Subduction Zone. One is evacuation drill, another one is questionnaire survey. So the questionnaire survey, we use mail-based questionnaire method. We send it out to 2,000 random selected household. We use 3 waves method. We totally collected 483 sample respondents from the 2 communities. And we have that yields about 30% response rate. So in this survey, we are able to capture people's risk perception, perceived knowledge, preparation, evacuation decision, evacuation logistics data, along with the demographic and the economical characteristics. So because of a time limit, I cannot show all the result to you, but I'm going to show you some, selectively show you some interesting result. So these red dots represent their respondents' location, their household location, relative to the inundation zone. So this is one interesting result from our survey. So this graph indicates how long people used to, is estimated to use before they evacuate. So on the y-axis is cumulative percent of the household. X-axis indicates the time in minutes they spend before they evacuate. So these 2 lines represented respondents from the 2 communities. As you can see that the answer from the 2 communities is very similar. There is no significant difference between the 2 communities. And about 65% of the residents say expected they're gonna spend less than 10 minutes to be prepared on the mailing time. And about 90 to 95% of people said they are going to spend less than 30 minutes on the mailing time. So I just mentioned about there are 2 communities, no significant difference on the mailing time between the communities. In contrast to that, so people's evacuation distance has larger difference between the 2 communities. So this picture depicts the evacuation distance from their home in the two communities. I divided this graph by the mode. The people evacuated either by food or evacuated either by drive. As you can see that the shorter line represent the distance people intend to evacuate if they evacuated by food. Majority of those people, if they evacuate by food, they are going to evacuate to within 1.6 kilometer. But in contrast to that, people who intend to evacuate by car, they're gonna evacuate a much longer distance. So about 80 and 90% of the people intend to evacuate within 5 kilometers. So those are some of those interesting information I want to show you about questionnaire. Then I'm going to show you how do we do the evacuation drill and how do we use that to collect the evacuation action data. So we organized the 6 evacuation drills from 2017 to 2018. We invited 136 participants to our drills. And we asked them we placed them to 7 popular locations, and we asked them to evacuate to outside of the inundation area to the 2 dedicated high ground area. So when they evacuate, we use GPS embedded cell phone to record their evacuation trajectory. And because we use that GPS trajectory, so we are able to capture their route choice, their speed, their destination, and their time they spend during the evacuation. On the right side, the heat map shows that the usage and density of that route. So basically, more red that route is, the more people use that route to evacuate. So because we have those GPS trajectory data, so we are able to build the walking speed distribution in response to this tsunami evacuation. And we're gonna use this distribution into our data model to inform the agent behavior. So we also analyzed what variables will impact the people's evacuation speed. So as I showed, so we use PADM model as a guideline to collect those protective action decision data, use the data to inform the agent-based behavior, and we also integrate the natural environment and building environment in our model. So we based on this platform, we test the different variable, we run different scenario and a Monte Carlo simulation, and we got some very interesting result. I cannot show all the results today because of time limit. However, I'm gonna selectively show some result. So the first result I want to show you is the mortality rate versus mailing time and the evacuation percentage. On the y-axis is the mortality rate. Y-axis mortality rate, x-axis is the mailing time in minutes. Different line represent the percentage of the people who decide to evacuate. So at the top dash line represent only 10% of the people who going to evacuate, and the lower line represent 100 people decide to evacuate. As you can see that from when more people decide to evacuate, the lower mortality rate is gonna be. But when you look at how does mailing time impact the mortality rate, you can see a Earth-shaped curve of each line. That means there is a nonlinear relationship between the mortality rate and the mailing time. So specifically, when we increase mailing time, the mortality rate increase. However, the marginal impact is different. As you can see that the S curve is on the top tail and the end tail of this S curve. That means is pretty flat. That means the mailing time has less impact on the mortality rate than the middle area of the mailing time. And so as you remember, we use the survey data to collect how people's intended decision on the two variables. And we calculated the 95% confidence interval of people's potential choices. They overlap the gray area represent and people's intended choice. And you can see that this area is not too bad, but we definitely has a lot of room to improve. As you can, so we could encourage people, more people to evacuate. That could decrease the mortality rate, and we could also encourage more people to immediately evacuate to decrease mailing time as much as possible. In that way, we can potentially save more people in this community. Another result I want to show you is a mortality rate versus the walking speed and the walking percentage. So y-axis mortality rate, x-axis is a walking percentage. And each line represent the different walking speed. So when you look at the two dashed line on the top, so that means when a walking speed, a walk percentage increase, that is more people choose to walk, the higher mortality it is. So that is very important because that suggests us if your walking speed is less than 1 meter per second, it's potentially better for you to drive than walk, even considering there is traffic congestion on the road. However, if your walking speed is faster than 1.5 or 1.3 meter per second, that's the 5 line at the bottom, that means you can potentially walk much faster than the car. And in that situation, as more people choose to walk, the much lower mortality rate it will be. So it is very important because it suggests to us that if you can walk fast, you can walk and leave out all the capacity to the transportation capacity, traffic capacity to the people who cannot walk fast, especially for the people who has disability and for the or other senior people who cannot walk fast. So if we can coordinate in that way, we can potentially save more people when the tsunami comes. So we have been talking about walking percentage, walking speed, also the mailing time and the evacuation decision percentage. So you can see that there are many variables we need to consider in this situation. And it's very difficult for a local authority to determine which variable has more impact or impact range than the other. So in order to solve this complexity, we created this tornado diagram to show how what the impact when we change one or multiple variable by controlling other variable constant. How does that impact on the mortality rate? What is the impact range of changing that variable impact on the mortality rate? On the lower panel shows the when we change one single variable but keep other variable constant, how does that change impact the mortality rate? What is that change range of the mortality rate? And the upper panel represent when we change multiple variable together, and what are the impact range on the mortality rate. let me give you an example. If we look at the panel, single panel, the mailing time, you can see that the impact range is from is this area, and so the middle line represent when we choose to use 10 minutes as our mailing time. So if we decrease our mailing time from 10 to 0, then that will decrease our mortality rate about extra 5%. And if we increase that to 20 minutes, that will increase our mortality rate about 10%. So, and you can see that mailing time has a much larger impact than the other variables, other single variables. But
Chen,
yes.
We're running out of time, soon, but we want to definitely leave some time for so Q&A. So wrap up this, your presentation in 1 minute or two.
Okay. Yeah, I am going to finish my presentation pretty quick, and I cannot exhaustively to talk about all the result of those tornado diagram today. But if you are interested, you can ask me later in the Q&A section. And so this result from the so this model can potentially benefit 4 groups of the practitioners. So they are city planners, social scientists, engineers, and emergency managers. Each of the group can use this model to use this model and the result to inform their programs and potentially help the evacuation preparedness in this kind of research. And at the end, I'm going to acknowledge my funding agency, National Science Foundation, and also thanks. And I want to say thank you to PacTrans to provide funding and presentation opportunities, and the conference and travel opportunities. And this is a Q&A section. If you have questions, you can ask me now. And if I cannot answer, I have my committee member here too. They are more knowledgeable than me to answer your question too.
Well, thank you, Chen. We used more time than initially planned, so feel free to fire your questions.
Maybe I can get started while other people are still configuring their questions. I think that's a very interesting talk, and I do think this research is highly important given the general background of global warming. So my first question is, which agent-based simulation tool did you use to conduct this research?
Yeah, so in our lab, we first used NetLogo as our agent-based model platform. But for my research, I use Julia. So Julia is a programming language. It's like Python. Julia as our platform language to create agent-based platform.
Okay, so this is something you build the simulation model from the scratch, or there's some open source network that you can just put on your actual stuff on the existing platform?
No, so we basically created from scratch. So they are. I didn't talk about more about agent-based model because we didn't have enough time. Julia, it has some package we can use, like the agent-based package, but there are some function we can use. However, about 80 to 90% of those content we created on the stretch. So there are, I didn't create all by myself. About 50% of this platform I collaborate with another colleague in our lab. So we created this platform by ourselves. Yes, in Taiwan.
Thank you.
Thank you. Thank you, Yinhai. Just very quickly, and the Julia is open source, and it's designed for agent-based modeling. It's a growing community. In Julia, it's for people who are knowledgeable about Python. It's easy to migrate, and But the limitation we had with NetLogo is the computational. This is when we involve like a whole citywide simulation involving, tens of thousands of agents. NetLogo tends to have a computational burden that we cannot resolve. So that's why we're, trying to identify alternatives to resolve that computational challenge.
That's right.
That's excellent. I think we need this kind of large-scale simulation model. There may be several options, each one with different emphasis. Some may be good at the road traffic, and some may be good at the geographical information. So I think it's kind of interesting to learn this particular platform, and maybe we can see how this may be useful for not just the disaster evacuation, but also for other research.
Of course. Yeah, this is a new tool for us as well. So we're, also learning at the same time of using it. Any other questions?
My second question, maybe it's not a very good question. I'm kind of curious about exactly what is the mailing time you are mentioning in your presentation?
Right. So mailing time. So mailing process refers to the process after an individual receive information from the disaster, such as the warning and maybe the environmental cues like the ground shake, and they receive from the time we receive the information until they make a decision. So it's so this process has a time. So we normally you can think about it's a preparation time. How long you use to prepare before you evacuate.
So this is a preparation time, not decision time.
Oh, so mailing time include the decision time and preparation time.
Okay, so basically that's the time duration since you received the message.
Exactly.
Receive the message.
Yeah,
and then started to evacuate.
Yeah, exactly.
Okay, thank you.
You're welcome.
This is a really good question. Yeah. Any other questions?
Well, I just sent a chat to everybody to feel free to unmute and ask questions. And while people do that, I have my little questions myself on the other end of what Yinhai was asking you. I appreciate the, very sort of challenging technical sort of issues. And I think this model is really fascinating. But when I'm thinking about the end sort of user, a person who could use this model to start planning for, the next sort of tsunami. For these people, you want to start by telling them that your model is going to establish a balance or relationship between mortality rates and different ways that people have to, quote unquote, escape. I'm using sort of a lay term, escape, the tsunami. So you start with that, telling them that you're measuring mortality rates, which is a very huge, kind of issue, very powerful. And whereas in our presentation, you told us at the end that that's what you were measuring. You understand? And then the other thing for communicating, I think, better with lay people would be to have your maps are terrific. The legends should be more prominent. You have some of the legends were very good, but sometimes they were absent. And so that's kind of an issue, for the layperson. Like these are very good, very, clearly explained, but some of the maps, with the dots and the colors did not have legends yet. And those are important because as you talk, the person needs, here. See, I need to know what those are in order to really follow what you're saying.
Got you.
But,
okay. That's a very good point. And thank you for the suggestion.
Well, let's see if others have questions. Because I was just trying to look at the other side of what Yinhai was talking about, because you're really spanning a huge area of interest, between policy and research. That's very challenging.
Just following what Yinhai asked earlier about the tool, And we actually, I should mention this clearly, that we have get a technology transfer, so grant support from PacTrans, and using that small grant that we were able to actually put the previous NetLogo model online on GitHub. Basically, put it in modular format. For people, for city. I mean, agent-based model, not everybody can handle that, with just no prior experience. So what we did use that, small grant is to, okay, if you just put your data in those modular, following that format, you are actually able to create a model for your community. But regarding the transportation network population distribution, and also the tsunami inundation, and plus some other input data. So keep it short is, we're trying to communicate the model and let the community to be able to use that, but this is a long shot. So appreciate PacTrans' support to make that effort happen, and it's still online. We are receiving information, we're receiving requests that for people that are asking use of that, not just in here but also internationally as well.
Well, I wonder if you could send me, and then we can distribute a sort of a summary of your research and where it's accessible. Any kind of links that you have that would be kind of useful, and then we can, forward that to the whole email list that we had, because people might want to click on these links and get more information.
Mm-hmm. So I think Ian had posted 2 other questions over here. When people has multiple alternatives for transportation, there might be a human choice problem. Do you consider this in your research? Chen, you can take this first.
Yes. So to answer this question, there are 2 aspects. So one is, yes, we do. So in this research, in this simulation, that platform, we do consider 2. Let me show you.
So 2 modes of transportation, basically, people walking on foot, and also people have the choice to drive. Exactly. But I think one thing I want to make it clear is that in this model, we didn't really incorporate. This is an ongoing effort. We haven't incorporated, say, for example, how the preceding earthquake has created damages to the transportation network, and the community that Chen is using is Coos Bay. As you can see from the earlier presentations, there are, it's really a kind of like an island. One of the accident route is US 101, which is like north and south, and if the earthquake that create damage that will causing damage to the bridges or to some of the other critical transportation links that connecting the city itself to the outside community, there will be a lot of challenges to use people to evacuate by car. And the community also have because of the river surrounding, and there's a dam over there, and that dam is also likely to have damage that may even create a secondary hazard, like say, for example, even flooding on top of the tsunami wave from that the dam. So only consider 2, but I think the message when we reach out to coastal communities to about this, we often just emphasize to evacuate by foot, and get high ground and leave early and cut the median time. Basically, don't waste too much time, and there's likely to be no warnings in the Cascadia event, and people have to use that strong ground shaking as the warning. They don't wait for warnings from the officials. There's likely be none. So I think there are some really critical messages.
I want to add 2 sentences to the mode choice, human choices, as you mentioned. So we did ask in the questionnaire, we did ask people, what's your mode choice when you're going to evacuate? And we calculated 95% interval. So the interval shows that about 16 to 27% people in Coos Bay, they are intended to choose walk, then drive to evacuate. Means that one fourth of people choose walk, 1/4 of people, third quarter of the people gonna choose drive intended people's choices in Coos Bay.
Mhm.
So we can compare that data with our simulation result, and we can use that comparison to inform local how do we improve how do we improve our evacuation outcome.
Yes, the other question that Yinhai posed over there is the coordinated evacuation actions. That's a really great point. And most of the coastal communities, they have some kind of, I wouldn't say every community have an evacuation plan, but some of them are they have a plan in existence, and some are in the process of creating their evacuation plan. And I think one of the, for the Coos Bay community, we're collaborating with the DLC Department of Land Conservation, and they have done some of the tsunami improvement project for the community. And we didn't, for the last part, we didn't really have, compared, the existing plan that the city has. How does that plan perform in the simulation yet? But one of the, powerful, potentially powerful useful, application is the city could use this type of tools to assess the effectiveness of their evacuation plan, and also identify, potential gaps. That are what potentially go well, what potentially not. And this is not a predictive simulation tool. It's more of like scenario. Under this different type of scenarios, if we just to test it in a simulation, and what are some of the likely outcome, and to inform the decision making at local, and maybe for emergency manager or even the city mayor for allocating retrofitting resources and investing. Basically smart use of the limited resources to, help improve the community resiliency in general.
Great.
Yeah,
Thank you
that's
for the
Bring
answers.
up about the idea of an evacuation plan is that in many cases, people only think of an evacuation plan as designated routes for particular neighborhoods. But in this case, the basis of the evacuation plan is don't wait. That is, the milling time should be as small as possible. You should pack a grab and go kit so that you can leave immediately. And the other one is that you should walk instead of take a vehicle. So there's already some parts of an evacuation plan that's really important, and that communities have already started implementing.
Mm-hmm.
It's a great point.
Thank you, Michael. Any other questions from the group?
I have a quick clarification question.
ahead.
So I saw that you're using instances for the population distribution. So I'm wondering, does the model assumes that everyone is at their home when the tsunami hits?
That's a very good question. Excellent question. Yes, we consider that. So this is a 1 hour scenario. Assume that all residents living at home. So that actually the question you ask is about temporal components of our model. So we can in some situation we can assume people is at work or even in the day or at night. So this one we assume people at home and assume it's at night.
So my follow-up question would be like, what would be different if the tsunami hits during the day? So if people are still at work, what would they usually do, and how would that change the scenario?
Right. That's
maybe let me take this one. I think this is a really fantastic question. I think this is a question not just for tsunami evacuation, for hurricane, for wildfire. All have this population distribution. I think particularly for the Washington coast and the Oregon coast, where general this Cascadia, we're talking about the residents who are living over there, and also a lot of tourists as well. I mean, not necessarily during COVID, but the regular time, a lot of people are visiting as well. So to keep it short, the model that we can incorporate both the residents and also visitors, but not necessarily in this model yet. But what we have done for city of Seaside, the northern coast, is to, visit the hotels and also, working with the city to identify, how many people are likely to be in a, like say, peak summer day, and the hotel capacity, hotel occupancy, and to also try to get capture that distribution of people who are visiting. So keep it short is, we need multiple different scenarios to do this. And for if it's happening overnight, it's happening over the day, happening overnight, the family are together. And if it's, over the day, the kids are in school and the parents are at work. So there will be a, like reunite process. So that certainly adds a lot of complications. So this is, I would say, keep it short is this itself is a big research question. And NSF actually has supported projects over the past few years, looking at the dynamic population distribution and for wildfires and for other type of hazards as well.
Thank you.
That's a great question. Any others?
I think we need to wrap up because I think Zoom is going to shut us off at the hour, doesn't it, Cole?
I don't think it will automatically kick us out. So
okay.
if we have more questions, we can take more questions, but we are also coming up on the hour that we had programmed. Yeah. So.
Mm-hmm.
But so we can go on, but I just want to say that any kind of questions that people may have to send to Chen or Haishang or me, and then we will forward, appropriately. And
yes.
then I think that Chen you're going to send us a little more information so that we can follow up on your presentation today.
Sure. I send my email at a chart. You can, if you have any further questions or just some suggestions, we can talk through email, and yeah. Or Anne, do you suggest?
I thought you had some links to some applications that you wanted to share with other people.
Yeah, we have. I'll work with Chen to get that. The GitHub that is currently still live and people are still accessing that, and I'll share that. Maybe that we can disseminate it in certain ways. So in case people are interested.
Sounds great. Is there one more question coming from the participants?
And I don't have a question, but I have a comment. I think that's a very impressive tool. I would recommend the researchers to consider how to move one step further to make it useful for the local agencies, because disaster evacuation is a big deal. We think the chance is low, but it's not that low for the West Coast, no matter from the tsunami perspective or from the earthquake perspective. I think it's going to be a good thing to make this accessible for practitioners and researchers. So thanks a lot for the excellent work.
Thank you, Yinhai, for that great comment. I think maybe I can just echo very quickly that we're using the Cascadia, the earthquake tsunami as a scenario or big context for this framework can really be applicable to wildfires or other type of hazards that are happening much more frequently. So I think that the key is not necessarily a particular event, but more of how do we use this type of interdisciplinary type of framework in our research. And this could be this also can be also applied. We're also using a similar to modeling traffic flow, mix the traffic flow with only human-driven cars, and versus there are autonomous driving cars in the flow as well. So that's also it's not disaster, but that can be done. And by bringing computer science and transportation engineering, and also the other aspect of human human behavior, human factor into the simulation. So it's it's really the framework can be transferable from one scenario to the other. Well, again, I would like to say just this. Thank everyone for your time to attend this out of a very busy week, and I'd like to see again that this is a great opportunity and also platform that a PacTrans enable, and for the PhD student, I think this will have long-lasting impact moving forward.
Thank you, everyone.
That's great. And stay tuned for the next PhD seminar.
Yes, I'll attend.
Thanks,
Thank
everyone.
you so much. It was
Bye,
wonderful.
everyone.
Have a good day.
Have a good day.
Bye-bye.
Thank you.